Hello, everybody. In this video lecture, we will cover bones and osseous tissue. So let me open up the PowerPoint. Okay, here we go. This is the PowerPoint that I will use. Let's go ahead and begin. So we're going to start with functions of the skeletal system. Skeletal system allow support of your body, and it also supports soft organs, protection, for example, cranial cavity for brain protection, vertebral cavity for spinal cord protection, and it also protects vital organs. For example, thoracic cage or rib cage protects your lungs and your heart. Heart is good protected because it's located in mediastinum, and mediastinum is the area behind sternum. So it's a nice bony protection of the heart. Skeletal system also provide movement. Your bones are levers for muscle action. So your muscle move bones, and that allow you to move your body. Storage. Bones store minerals such as calcium and phosphorus and growth factors. Blood cell formation. Blood cell formation is called hematopoiesis. And in the marrow cavities, in red bone marrow cavities, blood cells are formed, both red blood cells and white blood cells. And bones also store triglyceride, that is simple fat, as a source of energy. And it's stored in bone cavities. We call those cavities yellow marrow bone cavities. Two major groups of the skeleton based on location, axial skeleton and appendicular skeleton. On this diagram, axial is shown in brown color. So it includes skull, vertebral column, and rib cage, and appendicular shown here in yellow color. And it includes bones of upper extremities, lower extremities, and what we call girdles. This is pectoral girdle, include clavicle and scapula. And this is pelvic girdle, include a hip bone. And hip bone is made from ilium, ischium, and coccyx. Oh, I'm sorry, ilium, ischium, and pubis. Ilium, ischium, and pubis, and coccyx is a part of the axial skeleton, because we have 24 vertebra that are movable, and then sacrum, those are fused vertebrae, and coccyx, also fused vertebrae. So we can classify bones based on their shape. Bones can be long, they're longer than they're wide, short, cube-shaped bones, for example, in the wrist or ankle. So we call those bones in the wrist carpal bones. In the ankle, we call it tarsal. Sesamoid bones, example will be patella, and those bones are found within tendons. Flat bones, thin, flat, slightly curved, and irregular bones have a complicated shape. So it's really not that hard to understand if the bone is long. For example, the humerus, radius, ulna, femur, tibia, fibula, and even phalanges, right? Phalanges and metacarpal bones, metatarsal bones, they part of a long bone category. Short bones, we already mentioned, that is carpal bones and tarsal bones. Flat bone, for example, over here is a sternum. Many bones that make the skull, like frontal bone or parietal bones or temporal bones, they also considered to be flat bones. Irregular, giving over here is vertebra. The only maybe bones that might kind of be different to identify. For example, can be scapula. Scapula is a flat bone, and clavicle. Clavicle is considered to be a long bone. So clavicle is the only long bone that is located horizontally in your body, right? Because all these bones are vertical. So clavicle is a long bone. Scapula is a flat bone. Ribs are flat bones as well. Bone markings. Bone markings include bulges, depressions, holes that serve as site of attachment for muscles, ligaments, tendons. They also can be the surfaces for joints. And also, if you're talking about, let's say, foramina, those gonna be passages for blood vessels and nerves. When we look at bone texture, it can be divided into compact bone and spongy or cancellous bone. Compact bone is dense outer layer, and spongy is honeycomb or trabecular. So this is example of a long bone, and you can see on the surface, it is made of compact bone, and you would find spongy bone in a deep to the compact, right? So that's a spongy bone, and it's covered by compact bone. Also, if you look at microscopic structure, compact bone, another name is cortical bone. It's made from these circular units called osteon. So we see several osteons over here. Spongy bone is made of trabecular. And trabecular, this is what reminds us as sponge. That's why it's called spongy. Now we're gonna look at structure of a typical long bone. So long bone has a shaft that is called diaphysis, and two ends, they are called epiphyses. So we have proximal epiphysis, distal epiphysis, and diaphysis in the between. Diaphysis made of compact bone collar that surrounds medullary or marrow cavity. Medullary cavity in adults contains yellow marrow, right? So that's where we store triglycerides. Epiphysis, proximal and distal, those are expanded ends. Spongy bone interior. There is a line over here that is called epiphyseal line. And this is the remnants of growth plate. So when we are young kids or very young adults, instead of epiphyseal line, we have epiphyseal plate. And this is part of the bone where you would find cartilage. Bone actually can grow longer because of this cartilage in epiphyseal plate. So cartilage dividing and then bone getting longer, right? So imagine that this is the area where you have cells that are dividing. So this area allow your bone to grow longer, and then cartilage dies and ossifies. So cartilage is replaced by a bony tissue, and then you still have cartilage left, and it's divided again until we stop growing, right? At age maybe 18 for females in average, and 20 for males in average, this cartilage is all gone. And instead of epiphyseal plate, what is left, we have epiphyseal line, right? That means if person has epiphyseal line, that means his or her bones cannot grow longer anymore. Also on the surface of the proximal epiphysis and distal epiphysis, there is articular cartilage. This is a hyaline cartilage, and this cartilage form a joint. In this example, it's very specific joint called synovial joint. So hyaline or articular cartilage is a part of synovial joint. Also over here, you can see that there is a compact bone outside and spongy bone inside. Also, bone is very vascular organ. There is lots of blood vessels that supply your bone tissue or osseous tissue with oxygen and nutrients. Now, bone is covered by membrane called periosteum. So periosteum is the outer membrane covering the surface of a bone. Inside the cavity, we have endosteum. Endosteum cover bone cavities, and also spongy bone. So periosteum outside and osteum inside. Now, periosteum has an inner layer that is osteogenic layer. Osteogenic means it will be some cells that can divide, right? So the cells found in the inner layer are osteoblast, bone-forming cells, osteoclast, bone-destroying cells, and osteogenic cells. Those are stem cells. And those stem cells can differentiate into osteoblast. So this is inner osteogenic layer, and outer is fibrous layer. Right, so we have periosteum made from outer fibrous layer and inner osteogenic layer. And periosteum is attached to the bone by perforating fibers. So those are perforating fibers or Sharpey's fibers. Also, nerve fibers, nutrient blood vessels enter the bone via nutrient foramina. So if you see this is a nutrient artery, and there is a little opening here, right? That's called nutrient foramina. So these blood vessels can enter your bones. So endosteum is a delicate membrane on internal surface of bone, also contains osteoblast and osteoclast. So I already mentioned endosteum. So if you look here on this picture, they took a little piece of outer bone, right? This is a compact bone. We can see osteocyte in the lacuna, and here the periosteum. And the one that has fibrous layer and osteogenic layer or cellular layer. And if you look inside, the membrane that covers the cavity and spongy bone would be endosteum, right? So here's endosteum, and it also has osteoclast, osteoblast, and osteogenic or stem cells. Now, if we're talking about short, irregular, or flat bones, so this is how they would look like. So periosteum covered compact bone on the outside, so it will be periosteum, also the membrane. It will be endosteum that covers the spongy bone inside, and spongy bone in a flat bones called diploid. In between this trabecula, so that's the whole thing called diploid. Diploid is made from trabeculae, and between trabecula you would find bone marrow. So red marrow cavities of adults, we can find in the heads of femur and humerus, and trabecular cavities of the diploid of flat bones. And in infants, medullary cavity and all spaces in the spongy bone, this is where blood cells are formed, right? So when we very young, when we infants, then we have red bone marrow pretty much everywhere. All the cavities inside the bones, all medullary cavities contain red bone marrow. When we get older, this red bone marrow is replaced by yellow bone marrow. So we replace this osteogenic, hepatopoietic tissue, tissues that produce your blood, we replace it with the triglyceride, with fat. And when we adults, where we have left bone marrow, red bone marrow left is in the head of femur and humerus and in flat bones. Skeletal cartilages. Cartilages are also part of the skeletal system. They contain no blood vessel or nerves. What does it mean? If we have tissue without blood vessels, that means this is tissue that has, little regeneration ability. So really, if you damage, break, or fracture the cartilage, it would be difficult for cartilage to heal. So your bones are actually healed much better than cartilage. Also, cartilage are covered by connective tissue, dense connective tissue called perichondrium. And perichondrium contains blood vessels for nutrient delivery to the cartilage. So blood vessels found in pericardium, then blood vessels supply this cartilage with oxygen and nutrients by diffusion. So nutrients, oxygen diffuses to the cartilage, and waste product diffuses back to the blood vessels. There are three major groups of cartilage: hyaline cartilage, elastic cartilage, and fibra cartilage. Hyaline cartilage provides support, flexibility, resilience, and this is the most abundant type. Elastic is similar to hyaline, but hyaline cartilage contains okay, so elastic cartilage contains elastic fibers, and hyaline cartilage contains collagen fibers. Right, so in hyaline cartilage we would find collagen, in elastic we will find elastic fibers. In fibra cartilage we also have collagen fibers, and fibra cartilage is the strongest out of these three. So hyaline cartilage is the most abundant, fibra cartilage is the strongest, elastic cartilage is really only found in the pinna of your ear, in the epiglottis. So it's not very common type of cartilage. So in this diagram, you can see whatever shown in the blue color, this is hyaline cartilage. So you can see hyaline cartilage is a part of many movable joints or slightly movable. You would find it also in the costal cartilage. This is the structure that attaches your costa or ribs to the sternum. You find it in the synovial joints, right over here, here. Also, if you look at your respiratory system, larynx, trachea, then you have bronchi and bronchioles. So we have good amount of hyaline cartilage in those structures as well. Elastic cartilage found in external ear and epiglottis over here. So epiglottis is a structure that cover your larynx when you drink or eat something. When you eat your food or you drink water, this epiglottis will cover the larynx, so the food and water goes to esophagus instead of going to your trachea, instead of going to your windpipe. So that's our elastic cartilage. And fibra cartilage you would find between the vertebrae, right? It's intervertebral disc. And also this cartilage over here is called pubic symphysis. Right, so in pubic symphysis, also fibra cartilage is part of this. Now we're gonna look at microscopic anatomy of bone. The cell of bone include osteogenic cells. Those are stem cells in periosteum and endosteum that give rise to osteoblasts. Osteoblasts are bone-forming cells. So this osteoblast, they're gonna secrete bony matrix. because bone is osseous tissue. This tissue is made from cells and a pretty large amount of extracellular matrix. So cells inside a bone are not located close together, like, for example, in epithelial tissue. In epithelial tissue, we have cells and they connected even through some type of junctions. In osseous tissue, cells are not close together. There is a lot of space in between them, but it's not an empty space. In that space, you would find some organic stuff, inorganic, right? So osteoblasts are cells that secrete this matrix between the cells, between osteocytes. So here's a stem cell. This is osteoblast, matrix synthesizing cell responsible for bone growth. Another cells are osteocytes. Those are mature bone cells and they maintain the matrix. And osteoclast, cells that break down or resorb bone matrix. So here's mature osteocyte that maintains the bony matrix, and this is osteoclast, bone resorbing cell. And this one is multinucleated. So all this purple stuff that you see, those are nuclei. Now, osteocytes, so let me go back for a second. So osteoblast starts secreting matrix, and some of these cells became kind of surrounded by bony matrix. And when they completely surrounded by bony matrix, then they became osteocytes. This is microscopic anatomy of a bone, specifically compact bone. So structural and functional unit of compact bone is osteon. And osteon is made from these rings of bony matrix that called lamellae. Lamellae are weight-bearing, column-like matrix tubes. So you can see this is like one tube inside another tube and inside another tube and inside another tube. Right in the middle, there is central canal. And central canal contains blood vessels and nerves. So here's the central canal. Here's another central canal, right? And this is one osteon. This is another osteon. So what connecting those central canals are perforating canals. They at right angles to central canal and connects blood vessels and nerves of the periosteum and central canal. So let's look where we have perforating canals over here. So this one, this is perforating canal. This is perforating, and this one as well. And this vertical stuff, that's central canal. So perforating canals, they connect central canals, and they connect them with the nutrient artery that will be here, coming from outside and enters through the nutrient foramen. Lacunae. Lacunae are small cavities that contain osteocytes, and canaliculi are hair-like canals that connect those lacunae. They connect lacunae to each other and the central canal. So here, let's look at this diagram. So here's the structural unit, osteon. Right inside is central canal. Here's another osteon. Now those tubes, right? Those are lamellae. So here's the central canal. Here's perforating canal that connects central canal with the nutrient blood vessel over here. Now, like lacunae would be, let me see if I have next picture. Yeah, so over here you can see better. So this is mature bone cells, osteocyte. Now osteocyte are surrounded by pocket of fluid, and this surrounding fluid is called lacuna. It kind of like a little lake. So lacuna, inside the lacunae, we have osteocytes. We're talking about animal cells over here. animal cells cannot be surrounded by this hard mineralized matrix. So if you have cells and we surround it by matrix, the cell would die. So we need fluid surrounding every single animal cells. That's why osteocytes are located inside the lacunae. Now we want to bring nutrients from this artery. We want to bring oxygen and nutrient, let's say, to this cell. How to do it? It would be very hard for nutrients and oxygen to diffuse through this hard bony matrix. That's why we have these little channels, canaliculi. So you see this hair-like structure, a little canaliculi. So oxygen nutrients can go through this canaliculi to this cell, to that cell, to this cell, and so on. And the same is true for waste product. Right, so waste product can go back through this canaliculi back to the vein. So this is lamella, right? This is another lamella. This is another lamella. This is central canal. Osteocytes in the lacunae. Lacuna is one, lacunae is plural. And then we have canaliculus, one, or canaliculi, many of them. Right? Yeah, so that's, if you look over here, so this kind of dark structure over here, those are osteocytes inside lacunae, and it's like little feet radiating from the cells, those are canaliculi. If you look at a spongy bone is made from trabeculae. Trabeculae are a long line of stress. They do not have osteons. However, they do have lamellae. So here you see the lamellae, they are not that nice and circular, but those are, lamellae, those are structure made from bony matrix. And what is inside? Again, we have osteocytes inside the lacunae. And we do have canaliculi. Let's look at chemical composition of bone. So bone is made of organic part and inorganic part. Okay, so organic part includes, of course, cells. Osteogenic cells, osteoblast, osteocytes, osteoclast. We already discussed these cells, right? So organic part, cells. And another part of bone that is organic is osteoid. Osteoid is organic bone matrix secreted by osteoblast. So these cells, osteoblast, they secrete osteoid. And osteoid is made of ground substance and collagen fibers. Now, ground substance are made from proteoglycans and glycoproteins. So ground substance is made from proteins and sugar. And collagen fibers, those are proteins. They provide tensile strength and flexibility, right? So does it make sense? So osteoblasts secrete osteoid. All these cells and osteoid are organic part of a bone. Osteoid itself is made from ground substance and collagen fiber. So this is extracellular matrix. Osteoid is extracellular matrix. Ground substance are proteoglycans, glycoproteins, and fibers are collagen fibers. Now, inorganic part of a bony matrix are mineral salts. They make about 65% of bone by mass, and mainly it's a calcium phosphate crystals. Now, calcium phosphate crystals is called hydroxyapatite. So that's hydroxyapatite is the name for calcium phosphate crystals. And they're responsible for hardness and resistance to compression. So on this diagram, you can see bone and collagen and mineral components responsible for major functional characteristic of bone. Without minerals, bones would be too flexible. And without collagen, bones would be too fragile. So it's a perfect composition made from both inorganic and organic part. Bone development. Bone development is called ossification or osteogenesis, formation of bone tissue. Bone formation begins in the second month of development. Then we have postnatal bone growth until early adulthood, and bone remodeling and repair lifelong. So your whole life, your bones are constantly remodeling and repair. Right, so osteocytes maintain your bony matrix, right? Osteoblasts are constantly depositing new matrix, and osteoclast resorbing. So that's what remodeling would be. Now, when you, okay, so let's look back over here. Bone formation begins in the second month, right? So, well, this is our embryonic development. So what happened during the first months? If we develop bone in the second month, then what happened before? But before, embryo doesn't have a bone. Embryo has either a membrane where it's supposed to have a bone or cartilage. So ossification can happen through intramembranous ossification and endochondral ossification. Intramembranous ossification is formation of bone from a membrane. And this is the type of ossification that forms flat bones, like cranial bones and clavicle. So clavicle and cranial bones in the embryo, right, in the embryo, before the second month, they actually made of connective tissue membrane. And you know, when baby is born, we say baby has a soft spots in a skull. Those are called fontanelles. So those are fontanelles. It's actually this membrane that did not ossify yet, right? So imagine the skull of a baby that made from a membrane, not from a bone, and then this membrane became a bone. Clavicle is the only bone below neck region that is formed by intramembranous ossification. Everything else below the skull is formed by endochondral ossification. Endochondral ossification, when bone is formed from cartilage, and that it says the most of the skeleton. So here's an example of intramembranous ossification. So again, we're gonna start with the membrane. And this membrane, remember, this is still embryonic development. So those cells are called mesenchymal cells. Those are embryonic cells. Now, these mesenchymal cells, they can differentiate, and they will differentiate into osteoblast over here, and they start secreting bony matrix. And part of the membrane became a bone. This is called ossification center. And then we have formation of spongy bones, right? And finally, formation of the compact bone. So we're not going into details about intramembranous ossification. We just want to know that it starts with the membrane, mesenchymal cell that form center of ossification. Then mesenchymal cells, they will differentiate into osteoblast. Osteoblasts start depositing mineral salt. Then we have blood vessels growing inside, and spongy bone is formed. And then compact bone is formed on the surface, and periosteum, the fibrous layer, covered the flat bone. And we also want to remember that clavicle and cranial bones are the ones that formed by intramembranous ossification. Endochondral ossification uses hyaline cartilage models, and it's require breakdown of hyaline cartilage prior to ossification. So over here, again, brief introduction to endochondral ossification. that start with the hyaline cartilage model, then development of the bone color. So it's formed around the cartilage model over here. Then inside we have deterioration of cartilage matrix. So the cartilage start pretty much dying right inside. Because when we form this bony color, we really deplete the amount of oxygen and nutrients that can reach this chondrocytes. So these cells, cartilage cells, because of this bony color, don't get enough oxygen, so they pretty much start dying. And when they die, they form a cavity. Now, the special structure grows inside this cavity, and it's called periosteal bud. And what it has blood vessels, and it has osteoblast. So now cartilage is dying, and we have blood coming in finally, because you see no blood supply over here. That's why cells are dying. But when periosteal bud invades this area, here we have blood supply. And we have also osteoblast, right? So now osteoblasts start replacing the cartilage, and medullary cavity is formed. So this is called primary ossification center. Then secondary ossification center appears into epiphysis, both or sometimes only in one. Right, and also the blood vessels grow inside the secondary ossification center. So at the end, almost all this hyaline cartilage is replaced by bone, right? And whatever is left, epiphyseal plate, this cartilage will continue to divide and bone will grow in length. And another cartilage is left, articular cartilage on the surface that will form joints. Now on this picture, you can see two genetic conditions, achondroplastic dwarfism, that's this one, and cleidocranial dysplasia, this one. And those genetic disorders, they affect ossification. Achondroplastic dwarfism affects endochondral ossification. So bones that are formed from cartilage, they are not forming right. And people are dwarf. And especially they have shorter limbs, shorter arms and shorter legs compared to the rest of their body. Right, so this is problem with endochondral ossification. Cleidocranial dysplasia problem is with intramembranous ossification. And this disorder affects flat bones, right? Because if you go back, I'm just reminding you, intramembranous ossification, we have what? Formation of clavicle and cranial bones. So now in this disorder, we have problem with mandible and with clavicle. People can be born even without clavicle completely. So clavicle might be missing. Classification of bone fractures. Bone fractures can be classified by 4 either-or classification: position of bone ends after fracture, non-displaced or displaced, ends retain normal position or ends out of normal alignment, completeness of the break, complete, incomplete, broken all the way through if it's complete, or not broken all the way through, incomplete. Another name for this incomplete is green stick. Orientation of the break to the long axis of the bone, linear, so it's parallel to long axis, right? So it goes up and down. And transverse is perpendicular to long axis, so both right and left. And either it compound or open, or simple or closed. Compound bone ends penetrate the skin, and simple bone ends do not penetrate the skin. So here you can see several bone fractures, and what is used here is only one characteristic, but more than one can be used. So for example, this is transverse, right? And it's non-displaced. This is linear. This is oblique and complete, you can say. This is oblique and displaced. This is a spiral, green stick or incomplete. And comminuted means the bone is broken into several pieces. And we're gonna finish up with some homeostatic imbalances, osteomalacia and rickets. Those are problems with calcium salt deposition into bony matrix. The difference between them is that rickets are childhood disease. And because the young person is still growing, if he or her has this rickets disorder or disease, then, well, they're growing, they're getting bigger and heavier, and all this weight put lots of pressure on their legs. And very distinct characteristic of rickets is bowed legs and other bone deformities. Osteomalacia happens later in life, and because it's a condition of people who already grown-ups people, right, then it will not cause these bowed legs. The causes of osteomalacia and rickets can be vitamin D deficiency or insufficient dietary of calcium. So because the problem is calcium is not deposited, right? So either person doesn't have enough calcium in his or her diet, or they might have calcium in their food, but they lack of vitamin D, and vitamin D is necessary for deposition of this calcium inside the bones, right? So osteomalacia and rickets. Osteoporosis, loss of bone mass, bone resorption outpaces bone deposit. Spongy bone of spine and neck of femur become most susceptible to fracture, and risk factor include lack of estrogen, calcium or vitamin D deficiency, petite body form, immobility, low level of TSH, it's a thyroid stimulating hormone, or diabetes mellitus. And because risk factor include lack of estrogen, well, then because of this, osteoporosis is more often affects females, and especially elderly females. When females go through menopause and the level of estrogen declines, they became more susceptible to osteoporosis. So here you can see a normal spongy bone, and this is osteoporotic bone. So here's female in her, well, I believe maybe 70s, late 70s, and she has osteoporosis. If you look at her spine over here, that's a normal vertebra, but look at these two. They really lost lots of the tissue. And because of this, she has this hunchback over here, right? This is called kyphosis. So treatment and prevention of osteoporosis include calcium, vitamin D, fluoride supplements, increased weight-bearing exercises through life, hormone therapy, like estrogen replacement therapy, some drugs that increase bone mineral density. Okay, that might be our last slide. Let me go ahead and check. Oh no, we still need to talk about Paget disease. Okay, so let's look at Paget disease. Paget disease is excessive bone formation and breakdown. So you have lots of bone that is forming, but this bone is not strong enough to, and it doesn't have a right structure. That's why it cannot carry it on its function. Usually, you see this lady over here, he has like lots of bony structure growing here in her shoulder, right? So this is a Paget disease, excessive bone formation. Usually happen in the spine, pelvis, femur, or skull, right? So here you can see the, so that's a femur, that's a humerus. So here's the pelvis and darker part in the spine. Now, Pagetic bones has very high ratio of spongy to compact bone and reduced mineralization. And that's why those bones, Pagetic bones, very susceptible to fracture. So they can be broken easily. And of course, you know, this excessive growth of the bones that mostly spongy bone and has very low ratio of compact bone. Of course, it's, you know, it's not convenient. And if this can be broken easily, especially in this area, look in the pelvis, right, where we, you know, have, you know, good amount of movement, both in the pelvic girdle and in the pectoral girdle. So here's a pectoral, this is a pelvic girdle. So that's our joint here. So you have a lot of movement here and your bones are not strong enough. So it's easy to be broken right here or there. Cause is unknown. Possibly it's viral. And treatment include calcitonin and also the drug biphosphonates. And both of them, what they do, they just increase the deposition of the calcium inside this Pagetic bone because they're very fragile. Okay, so I think that's it. So this is the last slide. Very quickly, I want to remind you that we were covering bones and osseous tissue, and we talk about function of skeletal system first. We also said that skeletal system can be divided into axial and appendicular. The bones can be classified by their shapes. There is different bone markings. We also discussed that bone can be compact and spongy. We look at the structure of typical long bone. We also discussed the cartilages, right? 3 types of cartilages. We look at the microscopic anatomy, quickly, different cells, osteon, right, and structure of osteon. And we talk about chemical composition of bone, organic and inorganic. We cover briefly bone development that include intramembranous and endochondral ossification. We talk about classification of bone fracture, right? So we're here. And we finished up with osteomalacia, rickets, osteoporosis, and Paget disease. Okay, well, that's it for this lecture. Thank you for watching and hope it was helpful.